Can you guys hear me and see my screen?
Yes, sir.
Okay, so we started a little late, so we might have to move a little bit faster than usual. Okay, so in today's lab, we're going to be talking about what root locus diagrams using MATLAB and how the root locus can be used to achieve certain functions of a system. So I'm pretty sure I have not started root locus yet, right? Yes or no?
No, sir.
Okay, so let's start with the definition of the root locus diagram first, right? So suppose we have a system like this. So this is a closed loop system, and we have the open loop transfer function, which is HS, right? I mean, if there was no feedback path, then the open loop transfer function would be HS. And K is just a gain that is in series with the open loop transfer function, right? And what is the overall transfer function of the system? The closed loop transfer function? You just use the formula, which you already know, right? KHS divided by 1 plus KHS, and this is negative feedback, right? So this is the closed loop transfer function of the whole system. Okay, so now what we are concerned with are the closed loop poles, this one, right? So how do we get the closed loop poles of this system? I mean, this is the closed loop transfer function. So how do we get the poles?
We set the denominator equals 0.
Yeah, so denominator 1 plus KHS equal to 0 will give us the closed loop poles, right? Now suppose HS, which was the open loop transfer function, it's expressed as a function of S divided by another function of S, which is usually the case, right? So any transfer function can be expressed in this manner. So even if the transfer function is something like 1 by S, it's still a function of S in the numerator, right? Just by assuming it to be 1 into S to the power 0, right? And denominator is S, which is also a function of S. So any function can be expressed in this manner, transfer function, right? One function of S divided by another function of S. Now, if you substitute this equation in the equation for finding the closed loop poles, that means in this equation equal to 0, you'll get this equation, right? Very simple. And if you divide this equation by K, you'll get this equation. It's basically the same equation, but written separately because we need both of them. So these are the two equations that will give you the closed loop poles, isn't it?
Yes, sir.
Sir, is the lab being recorded?
I've already recorded it with another section, but still.
Okay, sir.
Okay, so these are the closed loop poles equation of the system, right? Now, what we are interested to learn is how the closed loop pole location varies with change in this value K, the gain, right? So that is basically what's called a root locus. So you already know what the word locus means. It means what? How the location of something changes, right? The location of something, that is locus, isn't it? So in root locus diagram, we are concerned with the location of the closed loop poles. We're concerned with the location of the closed loop poles and how they change with the value of this gain, K. So let's start with the lowest possible value of K. So when K equal to 0, right? So put K equal to 0 in the first equation, you'll get AS equal to 0. Right?
Yes, sir.
And if you put K equal to infinity in the second equation, you'll get BS equal to 0. So we have the highest possible value of K, which is infinity, and the lowest possible value of K, which is 0. And for each, we have two separate results, right? Now, what is AS equal to 0? What does AS equal to 0 represent? So if you take a look at this transfer function, which is the open loop transfer function, what does AS equal to 0 represent? When K equal to 0, AS equal to 0. And AS was the denominator of the open loop transfer function, right? So what does AS equal to 0 represent?
Poles. Poles.
Poles as well.
Open loop poles, right?
Yes, sir.
because this is the open loop transfer function HS, right? And when k equal to infinity, Bs equal to 0. So what does Bs equal to 0 represent?
Zeros.
The open loop zeros, right? Now, what does that mean? As we change k from 0 and as we increase it up to infinity, the closed loop pole location, it will start from the open loop poles and it will end up at the open loop zeros. Because again, remember, these results were obtained from the equation for the closed loop poles, which was 1 plus KHS equal to 0, right? That's how we got these two equations in the first place, right? By equating 1 plus KHS equal to 0. So basically the closed loop poles. And by changing the value of k, which is the gain in the forward path, the closed loop pole location can be changed from the open loop poles and they will end up at the open loop zeros. So do you understand this part?
Yes, sir.
Yes, sir.
So that is the definition of the root locus. So basically this line is the definition. If we change the value of k from 0 to infinity, the closed loop poles start to move from open loop poles represented by as equal to 0, and they will end up at open loop zeros, which is represented by bs equal to 0. And this is the definition of the root locus. That's how we can manipulate the location of the closed loop poles by changing the value of k. Is it clear?
Yes, sir.
So why do we want to do that? I mean, what advantage is there if we want to, for example, we change the location of the closed loop poles by changing k. What advantage does that offer? Any possible
So it
advantages
can go
on that?
from unstable to stable.
Yeah, we can make an unstable system stable. We can change various other parameters, right? Like overshoot, rise time. All of these factors depend on the location of the closed loop poles. You should know this, right? Because you have studied second order systems in the class. So you know that closed loop poles have a variety. The location of the poles have a variety of effects on the system. It determines how fast is the system response is, whether the system rises exponentially or decays exponentially, whether the system is stable or unstable, etc. The damping of the system, right? All of these are determined by the closed loop poles. That means the poles of the system, right? And if we can manipulate the position of these poles by changing the value of k, it can provide a lot of advantages, right? So up to this part, any question?
No, sir.
No, sir.
Okay, so let us take a look at an example now, how we can use the root locus diagram to our advantage. So this is an open loop transfer function. Remember, don't confuse the word open loop with closed loop. They're different. Closed loop is formed with a feedback, and open loop is just without any feedback, right? So this is the open loop transfer function, an example. So let's plot the root locus diagram first. So give the num and the den. Then the den, in this case, you can do it by multiplying these four factors and writing the coefficients one by one, which is time consuming, or you can just use conv, right? So conv two of them, conv the other two, and then conv the results with each other. Very simple, right? Then use the function r locus num comma den. So this will give you the root locus diagram. So I've already So I've already written this code down from a previous lab. So let's run this part. So we have num, den, r locus, right? Okay, excuse me for a few seconds. I have a call. Okay, so this is the root locus diagram. So this is at pole zero plot first of all. So if you take a look at the transfer function, how many poles are there?
4,
4 poles, and how many zeros?
1.
Yeah, so these are the open loop poles and open loop zeros, right? And we have these 4 poles, 1, 2, 3, 4, and the open loop 0. Now, there are a few rules for drawing the root locus diagram. The first one you already know. The first rule is that the closed loop poles start to move from the open loop poles and ends up at the open loop 0. So this is the first rule. So in every case, you'll see that one pole will move to a 0. Now you may ask, there are 4 poles and 1 0. So how is that possible, right? Can anyone tell me? I mean, we have 4 poles and 1 0, but the poles should all move towards the 0, right? According to the root locus definition. So where will we get the 3 extra zeros? So we have to assume that those 3 extra zeros are located at infinite locations. So if you take a look at this pole at minus 20, you'll see that it's moving towards the left to a 0, which is at minus infinity. This pole, this is moving towards this 0, right? Normally. This pole and this pole, they will first move towards each other, and then they will diverge from this point. One will go up, one will go down. So one will go to a 0, which is at plus infinity, and the other will go to a 0, which is at minus infinity. So this is the first rule. The poles will move towards zeros, right? Now the second rule, I mean, there are many rules. We'll just discuss the basics of them. The second rule is that the root locus diagram will only exist to the left of an odd number of poles or zeros. Again, the root locus diagram will only exist to the left of an odd number of poles or zeros. So let's start with this pole. So this is pole number 1, right? Which is an odd number. So the root locus diagram will exist towards the left of this pole. As you can see, this is the root locus curves. So they exist in this location. Now let's move on to the next pole, pole number 2, which is what? An even number, right?
Yes,
So
sir.
nothing will exist to the left of this pole. So as you can see, there is nothing, no root locus. Now this is pole or 0 number 3. So what will happen now?
It will go left.
I mean, it not that it will go left, it's just that the root locus will exist towards the left of this 0.
Yes,
Right?
sir.
And this is pole or 0 number 4, even number, nothing exists. Again, this one, pole or 0 number 5, odd number, the root locus exists. So since now you know the locations where the root locus exists, now you can do your drawing. So move each pole to a 0. This pole will go to this 0. This pole will go to a 0 at minus infinity. These two poles will move towards each other and then go to plus and minus infinity respectively, but not in straight lines, as you can see, right? They're moving in curved directions, and they're moving towards each other. So that's a rule which you have to follow. Then you have to find out the angle of departure, basically, which is the angle at which they leave. And these are not important for the lab. In the lab, you might just have to know how to draw a basic rough sketch. But I think in your theory class, you need to learn how to draw an exact root locus diagram. There are many formulas to do that, to find the root locus, for example, to find the point where they diverge. I think there's a formula for that. To find the angle at which they leave, I think there's a formula for that. And as you can see, they're moving in sort of a curved line. So you have to find the asymptote to which these lines are parallel, right? You have to find the equation of the asymptotes in this case and also in this case. So there are also formula for that, to find the equations of those asymptotes to which these curves are parallel. Is it clear?
Yes, sir.
So that is the root locus diagram in a nutshell. Any questions?
Sir,
Yes.
sir, suppose my pole is in location 1 and my 0 is in location 2. Then in that case, the pole 0 counting, will it be for like 1, 2, or for 0, I will again start counting from 1?
No, this is basically you start from the rightmost pole or 0 and just start counting. That's it.
Okay.
It doesn't matter if it's a pole or 0. Just count all of them, and to the left of an odd number of poles or zeros, the root locus will exist. To the left of an even number of poles or zeros, the root locus will not exist. That's it. Any other questions?
Sir, why are they diverging towards positive and negative infinity?
That's just one of the rules of the root locus diagram. I mean, there's no scientific explanation for that.
Okay.
Yeah. I mean, you'll learn how to calculate these departure angles, the asymptote equations, diverging points, etc. in the class. But in the lab, you don't need to know those things in detail. Okay, should I move on to the next part? Okay, so we have plotted the root locus diagram. Now let's make use of the root locus diagram, right? Let's make use of it to achieve some desired parameters of the system. Suppose we want to design that system with these two parameters. The overshoot should be less than 5%. Rise time should be less than 1 second. Both of these are good things, right? I mean, the overshoot should be as low as possible always. And the rise time should also be as low as possible, which will to ensure that the system has a fast response. Right?
Yes, sir.
So in order to do that, you need to learn two more formula. So the first formula is for the damping ratio, which is related to the percentage overshoot. The second formula is for the natural frequency, which is related to the rise time. So do you know what these parameters are, the zeta and omega n?
Yes, sir.
So where did you study them? What are they?
In second order system.
So you saw them in the generalized equations for second order systems, right?
Yes, sir.
Yes, sir.
These two parameters, yeah. So they have a lot of factors. Depending on their values, the system will have different properties. But now we are concerned with to obtain these two parameters, right? And for that, we need to calculate the damping ratio given by this formula, where PO is the percentage overshoot in percent. So directly 5, not 0.05. You have to put 5 here. And this is the omega n, natural frequency, 1.8 by rise time. So place these two values, 5 and 1, in these two formula. So you'll get two values for zeta and omega n. These are the values. So zeta equal to 0.7 and omega n equal to obviously 1.8, because 1.8 by 1, 1.8. And you have to take note of whether they should be greater than those values or lower, right? So if you, for overshoot less than 5%, that means if you put 5 in this equation, you see that damping ratio should be greater than whatever value you obtain. So zeta should be greater than 0.7. And for rise time less than 1 second, this one is very simple to see. Just put TR equal to 1, but it should be less than 1. So omega n should be greater than 1.8. So zeta should be greater than 0.7 and omega n should be greater than 1.8. So these are your two conditions to achieve these two desired parameters, right? Now you also need to know the geometric definition of zeta and omega n. I think you have studied this. Do you know? In a root locus, I mean in a plot, in a pole zero plot, what is zero and what is omega, what is zeta and what is omega n geometrically?
Yes, sir.
Zeta is the cos theta.
Zeta is the cos theta, and what is the theta? The angle made with the negative x-axis, right?
Yes.
And what is omega n?
So
It's
vertically,
basically- No, it's just the distance from the origin. Distance from s equal to 0.
yes, sir.
Yeah. So the geometric definition, zeta equal to cos theta, where cos theta is where theta is the angle that the pole makes with the negative x-axis, and omega n is the distance of the pole from the origin directly, right? So using those two geometric definitions, we want to select a particular point in the root locus diagram which will satisfy these two values, which is zeta should be greater than 0.7, omega n should be greater than 1.8, so that we can achieve these two conditions. So let's run these three lines. So zeta, omega n, and S grid. So S grid will plot both zeta and omega n on the root locus diagram. So this is the root locus diagram that we have already obtained previously. So now let's plot these three lines, run these three lines. Any changes in the root locus diagram?
No, sir.
Yes, sir.
What is the change?
There are some numbers.
Yeah, so we have a new semicircle and two lines, right? Let's zoom in. So can you tell me what the semicircle represents just by looking at the figure itself and the values?
Sir, omega n.
Yes, it represents all the locations which are at a distance of 1.8 from the origin, right? That means a semicircle with a radius of 1.8, isn't it?
Yes, sir.
So in the upper direction, you see 1.8 distance. In this direction, you can see 1.8 distance. Towards the left, you'll also see a distance of 1.8, right? So this represents a semicircle with a radius of 1.8. That means omega n values of 1.8 are represented by this semicircle, right? And these two lines, these two straight lines,
Zeta.
yeah, they represent zeta, where zeta equal to cos theta, where theta is the angle made with the negative x-axis. That means this angle and this angle, right? Both are equal to the same theta value, same angles, right? This one and this one. And the cos theta value for those angles is 0.7. Is it clear?
Yes, sir.
So again, what was our condition? Zeta should be greater than 0.7. That means cos theta should be greater than 0.7. And omega n should be greater than 1.8. So, okay, let's look at the bottom condition first. Omega n should be greater than 1.8. So where should we select this point? Omega n greater than 1.8.
Outside the circle.
Outside the semicircle, easily, because the semicircle represents 1.8. So we want greater than 1.8. So outside the semicircle. And this one, cos theta greater than 0.7.
So inside the triangle.
Or outside the two straight lines.
Within the two straight lines, right? Between the two straight lines.
Yes, sir.
Because we know that if theta is lower, cos theta will be higher, right? Since these theta values represent cos theta equal to 0.7, if we select a lower theta than these theta, we'll get cos theta greater than 0.7. Right?
Yes, sir.
Yes, sir.
So overall, how will we satisfy both these conditions overall? Which point should we select?
Sir, inside the two straight lines and outside the semicircle.
Yes, outside the semicircle and within these two straight lines. I mean, you can extend them a lot more. So just extend them, and you have to stay between those two lines and outside the semicircle. So for example, this point, it works, right?
Yes, sir.
Yes, sir.
What about this point?
No, sir.
No, sir.
No, sir.
No, because cos theta will now be less than 0.7, right? Okay, so you know how to select the point. So let's select the point. So for that, you need to use rlog_find, which will allow you to interactively select any point in the root locus diagram. And you'll get two output parameters. K will give you the gain that is associated with that location. That means your forward path gain, which we saw in the first diagram, K. and poles. So it will also give you all the closed loop poles associated with the point you have selected. That means with the gain that you have obtained, it will show you all the closed loop poles, right? So copy, we don't need to copy, we already have this line. So let's run. Now you can see that there's a pointer which we can use to select any point, right? So let's select here, for example, this is correct, right? Outside the semicircle and also within the two lines at this point. Okay, I've clicked. Now if you take a look back at the command window, you'll see the selected point, which is this one. And now if you type K, you'll get the gain that is associated with that point, 373.24, and poles. So these are the 4 poles that you obtain if you use a gain of 373.25. So you'll get these 4 poles, closed loop poles. Okay, so now let's check whether anything has changed. So let's check whether these 2 conditions have been satisfied or not. So these were the closed loop poles, gain for the closed loop poles, right? So if you take a look back at the original block diagram, this is the main block diagram, right? So HS is the open loop transfer function, K is the forward path gain which we have just obtained, and we have a negative unity feedback, right? Now let's obtain the closed loop num and den, because our system so far has been open loop, right? So this transfer function original, this is the open loop transfer function, right? So now we have to make it closed loop by including this gain. So you can easily do that using the formula that you already know, but there's an even easier function in MATLAB called cloop or cloop. So this will give you the closed loop num and den from your open loop num and den. And this will assume that you're making a system unity feedback. So you're making it closed loop just by adding a unity feedback path, right? And don't forget the gain, which is also in series with the open loop transfer function. So you have to multiply the numerator of the open loop transfer function with the gain K. So this is the new, this is the overall open loop transfer function now, including the gain, and just use cloop to make it closed loop. That means you'll it will be assumed that you're adding a unity negative feedback path, and you'll get the new num and the new den. So let's run this part. So you'll get the new numerator and the new denominator, closed loop numerator and the closed loop denominator. Now if you just plot the step response using those numerator and denominator values of the closed loop transfer function. So this is the overall step response of the closed loop system. That means the overall system. Now, how can we check whether these 2 conditions have been satisfied or not from this diagram? Overshoot less than 5, rise time less than 1. How can we do that? How can we do that?
We can take the overshoot from the figure.
We can?
So there is a very little overshoot in this case. We can see that.
Yes, I mean, yeah, we can see that. I mean, with our eyes, we can say maybe those conditions have been fulfilled. But how to use this figure? I showed you in the last lab, I think. Yeah, I did. Is there any way to get the values from this figure directly?
There is a pointer that gives us the values.
Yeah, but that is very cumbersome. Why don't we just right click, then click characteristics, then you can choose these parameters, right? Do you remember this one? I showed you in the last lab, a shortcut method. Anyway, right click characteristics. So let's select rise time first. So rise time will be taken from this point to this point. I think they're using the 10 to 90% definition. So if you hover above this point, you see the rise time, which is 0.9 seconds. So this condition has been fulfilled. And the overshoot is very easy to see, it's 0, but still, click peak response. You'll get the peak value, which is 1, and the overshoot, which is 0.07%. So has our conditions have our conditions been fulfilled, both of them?
Yes, sir.
Yes, sir.
Okay, so that is the advantage of applying the root locus diagram. Just by changing this k value, the gain, our original open loop transfer function was num comma den, but just by adding this gain k, we obtain these two desired parameters, right? So that is how we can utilize the root locus diagram and manipulate the location of the closed loop poles to achieve our desired system response. Okay, so this is another one which you'll do as your lab task. 1 by ms plus b. Rise time, you have to fulfill these two conditions like the previous one, same method. But steady state error less than 2%. You cannot do that using this method, right? So for the to reduce the steady state error, you need to add another component in the block diagram. So this is control of steady state error by using a lag controller. So we can add a lag controller with the system to control the steady state error, right? Okay, so what is a lag controller? So this is the general transfer function of a lag controller, s plus z naught divided by s plus p naught. There's also a thing called a lead controller. So depending on the value of z naught and p naught, it can either be a lag controller or a lead controller. So have you heard these? Have you studied this controller in the class?
No, sir.
No. So basically, if your z naught value is greater than p naught, that's a lag controller, and vice versa, lead controller. Right? So this lag controller will be connected in series in the forward path. If we insert this term in the forward path. So basically, in this forward path, KHS will add the lag controller also in series, right? Now, if we add the lag controller in series, so this is the transfer function that we'll get if we multiply this with 1 by ms plus b. So we're studying this one, 1 by ms plus b. So if you multiply 1 by ms plus b with this one, this is the overall transfer function. We have not added the gain k yet. This is without k, right? So this is the overall transfer function after adding the lag controller. Okay. So now let's see how the lag controller operates. So let's select the values of m equal to 1000, b equal to 50 for this open loop transfer function. U equal to 10, we'll come to this one later. Okay. Z naught and P naught. Now again, as I mentioned, for a lag controller, Z naught should be greater than P naught. So, but just by looking at these letters Z and P, what do these two represent? Z means a 0. That means you are adding an extra 0 with the overall system. And P represents a pole. We're adding an extra pole with the overall system. Right? That is why they're represented by Z and P. Okay, so I've written this line for better understanding. Now, tell me, how does a lag controller reduce the steady state error? It will reduce the steady state error, which we'll observe later on by running this code. But let us define how it does it. So, can anyone tell me? Read this line first. Read the blue text. And then tell me how the lag controller can reduce the steady state error. Do you remember this one from the previous lab at least?
Yes, sir.
Did I not show you that if we increase the system type, I think it was also part of your lab task.
Yes, sir. If we increase the number of poles, it becomes stable.
Not the number of poles, if we increase the system type, that means the number of poles at the origin.
Yes, sir.
Yeah, if that means if we increase the system type, the steady state error will decrease. That is the general trend, isn't it?
Yes, sir.
So that is what we are doing here. We are adding an extra pole, not at the origin exactly, because adding an extra pole at the origin will increase the system type. That is what we want to do. but we are adding an extra pole at minus p naught, right? So if you equate this equal to 0, s plus p naught equal to 0, we are adding at minus p naught, right?
Yes, sir.
But if you take a look at the value of p naught, it's what? 0.03. So can you not say that this is approximately equal to 0?
Yes, sir.
Yes, sir.
So you can say that we are adding an extra pole at the origin approximately. That means we're increasing the system type by 1 approximately. That means we can reduce the steady state error. Do you understand?
Yes, sir.
Yes, sir.
So that is how we reduce the steady state error, by adding an extra pole close to the origin. Now you can ask me what is the use of the numerator? Why do we need s plus z naught? Why do we need this term? Can anyone tell me by reading this blue text one more time?
Sir, adding an S means adding a pole at 0 origin.
একটু জোরে বলো, বুঝি নেই।
স্যার মানে S গুণ করা মানেই তো স্যার মানে আমার 0 তে একটা পোল বাড়ানো।
Yeah, that is we are adding a pole by inserting this term s plus p naught. We are adding an extra pole close to the origin. But why do we need s plus z naught?
So that the overall transfer function doesn't change much.
Yes, that is what I've written here. So that the overall transfer function doesn't change much. So why is that important? Because again, this is our system. We have to do our work with this system. If we change the system, then we might just change the system design, what it was originally used for. We cannot just do that, right? We cannot change the actual system. Otherwise, it might not give us the proper function, isn't it? That it was designed for. So we cannot change the overall transfer function of the system significantly. I mean, we have to change it a little bit, right? Otherwise, we cannot do this. So that is why we are adding an extra 0, s plus z naught, which so a 0 is added at minus z naught, right? So by adding an extra term, we can ensure that the overall transfer function of the system does not change by much. And how is that possible? Because as you can see, these two values are very small, right?
Yes,
I mean,
sir.
p naught is obviously super small, close to 0, but z naught is also fairly small. So you can say that this overall transfer function approximately equals to almost 1, right?
Yes, sir.
Not 1, but close to 1. So that means we are not changing the overall transfer function of the system by a whole lot. But again, you have to remember, if you make z naught very close to p naught, what will happen? They'll just cancel each other out and will not get the effect of the extra pole. That's also a problem, right? You understand what I mean? If you make z naught equal to p naught, for example, that means we are not actually doing anything to the system. We're just adding a 1.
Yes,
Yes,
sir.
sir.
Yeah, so that's also a thing we have to look out for. You have to choose a balance so that z naught is much higher than p naught. That means it's not close to p naught. But you also have to ensure that the overall system transfer function doesn't change much. So do these two values fulfill those conditions?
Yes, sir.
How? First of all, they're very small, so this overall transfer function is close to 1. But again, if you take a look at z naught, it's 10 times p naught, isn't it?
Yes, sir.
So that means that z naught is very, very, very far away from p naught. This is equivalent to 3 being very far away from 30. Same thing, right?
Yes, sir.
Would you say that 3 is very far away from 30 on the x-axis?
Yes, sir.
So you can also say that 0.03 is very, very far away from 0.3. So that means this 0 will not affect the workings of this pole. That means we are adding an extra pole. That means we're managing to increase the system type almost by 1, close to 1.
Yes, sir. Clear.
So is it clear? So is it clear how this lag controller operates? Just the basics at least.
Yes, sir.
Any questions from anyone? Okay, so now let's verify whether this actually works or not. So we have obtained this one by inserting the lag controller. So let's run up to this part. We have the num and the den, new numerator and denominator represented by this. So I think this is this code. So up to this part, let's run. Let's okay. Now let's plot the root locus diagram, because we need to select a point that will give us the desired rise time and overshoot. And for that, we need to first obtain the root locus diagram. So in the same manner as the previous example, sorry, I just use our locus. And then we have two values which you have to calculate, S grid, zeta and omega n, right? So these were the conditions: rise time less than 5, overshoot less than 10. So for that, these are the zeta and omega n values that we obtain. If you insert this in using insert those values in these two formula, you'll get those two zeta and omega n values, and use S grid so that those are plotted on the root locus, and then use rlog find to select a desired point, right? Okay, so let's run this section. So again, we have obtained the root locus diagram and also the what zeta and omega n locations, basically, right?
Yes, sir.
Just by looking at this root locus diagram, the colored portions are the root locus, right? Do they are they consistent with the rules that we learned? What were the rules? Poles will move to the zeros and to only to the left of an odd number of poles and zeros, right?
Yes, sir.
So does it follow those two rules, this root locus diagram?
Yes, sir.
Yeah, so as you can see, there are two poles and a zero, as far as I can see. So these two poles, one pole will move towards this zero, and the other pole will move towards minus infinity, represented by the green line, right? And it only exists to the left of an odd number of poles or zeros. So pole number 1, it exists. Pole number 2, nothing exists here, right? Then pole or zero number 3, again, the root locus exists. So this was just a verification whether that rule is true. Anyways, so by the dotted semicircle and the dotted lines, they again show our zeta and omega n values. So where should we select the point?
So inside the lines, outside the circle.
Yes, inside the two lines and outside the semicircle. Not semicircle, I think this just a segment of a circle. Anyway, so suppose we select a point here. Is this correct?
Yes, sir.
Okay, so let's click. So we have obtained values of k. In this case, it's kp. What is the next part? Now we'll just verify whether all those three conditions have been fulfilled or not, right? Because we have already added the lag controller. Same method as before, new figure, new time range. But these two lines, numc and denc. So previously we used cloop, right, to make the system closed loop. Here, what has been done in this code is that only the formula has been used, the formula that you know for negative feedback directly. And after using the formula, these are the numerators and the denominators of the overall transfer function, including the lag controller and also the gain kp, right? So this is the overall num and den. We didn't use cloop, we just used the formula. If you use the formula, you'll get this result. You can do it by hand if you want, right? So let's run this part. Okay. Evaluate selection. So this is the overall step response, right? So let's select characteristics one by one. Rise time. It's 1.53 seconds, which is much less than 5 seconds. So that has been fulfilled. Oh, which figure was it? This one. Overshoot. Overshoot is 10.4%, right? What was the condition? Has it been fulfilled?
No, sir.
No, but it is close. It's close. It has not been fulfilled, but it's close. It's near to 10%. Now the thing is, I'll explain. I'll move on. Go back to this part. Let's check the last thing, which is the steady state error, right? So right click steady state value. The steady state value is 9.95. So, but this is the step response. So what is the steady state error?
0.05.
I mean, how? I mean, isn't the step input 1?
Yes.
There is a gain.
So that's where the u comes in. Remember at the start of the code u equal to 10.
Yes.
We gave u equal to 10. And if you closely take a look at this step line in the last line, you see that this u has been multiplied with the transfer function. Do you see it?
Yes, sir.
So we're adding we're directly multiplying a 10. That means we're using the step value of 10, not 1. So the input was 10 basically, and the steady state value of the output is 9.95. So what is the steady state error?
0.05.
0.05, which is equal to 5%.
5%.
So has that been fulfilled?
No, sir.
I don't think it's, is it 0.05 or 0.005? I mean, is it 5% or 0.5%? Can anyone please calculate this one? The percentage difference between 10 and 9.95. I mean, just make it a percentage. I don't think it's 5. I don't think it's 5%. If it were 5%, I think it should have been 9.5, right?
0.5%.
It should be 0.5%, isn't it?
Yes, sir. Yes, sir.
Yeah, so the steady state error condition has also been fulfilled. It's less than 2%. So all three conditions have been fulfilled, but the overshoot not exactly. Now the reason for that is these two formula that we have for zeta and omega n, these are not exact formula. These are approximate formula. So sometimes if you select a point which might seem correct, you might still not get the desired results. So how to fix that? Just choose another point. That's it. You might not always get the desired result, even if you select the correct geometrical point. Is it clear?
Yes, sir.
Okay, so that is the end of this lab, a fairly short lab today. Any questions?
So why did we multiply u?
I don't know. I mean, it was this lab sheet, whoever made it, he did it. I don't know, no reason. You don't need to do it. You can just, without it, you can, if you do it with 1, you'll get final value 1.
So how are we controlling the steady state error by lab controller value? I mean, it said less than 2%. I mean, where did we calculate that?
Where did we calculate the steady state error?
No, sir, it said less than 2%. If it said less than 1%, what would be the change in Z0 or P0? How would we calculate it?
So for that, you have to maybe do some trial and error, select the appropriate values of Z0 and P0, right? Maybe in this case, you want to make P0 even closer to 0, but you cannot give it exactly 0. Otherwise, it will be tough to not change the overall system transfer function. In some cases, you might not be able to go below a certain value. Maybe that might also be the case. So these are the two main things. You have to select the appropriate value of Z0 and P0. We'll learn much better methods in the next lab. Don't worry. In using Simulink. Yeah. Any other questions?
No, sir.
No, sir.
No, sir.
Okay. So now your lab task, do this cruise control system on page 4. This is your transfer function. You have to fulfill rise time less than 5 seconds, overshoot less than 10%. You do not need to do the steady state error part. Do this part in the same manner that we have already shown in the previous example, right? And attach the screenshots in a Word file. The screenshots should be of your code. You might just copy paste the code if you want. your graph and your results, and you have to show on the figure that these conditions have been fulfilled. So right click characteristics, etc. So that is your lab task. You may start. And you have to upload in the assignment section, which I'm giving right now.